Okay, this is part 3 of integrating. And really I'm using integrating, but the goal here is to take our ground reaction force and then create position, velocity, and acceleration. So remember Newton's second law, we add up all the forces acting on the object, and we understand the product of mass of the object and the acceleration due to the acceleration of the center of mass. Okay, and that's important. And so when we're doing human movement, as long as we're measuring all the forces acting on the person, we can calculate the position, velocity, and acceleration of the center mass of the person. But it's the center of mass. It's not the legs, it's not the arms, it's not the trunk. We have to remember that. And so when you're looking at ground reaction force, you have to remember that you're looking at center of mass kinematics, all right? F equals ma, where A is center mass. But, and the other key here is to be able to do this successfully, we need to be able to measure all the forces acting on the person. So if we're doing running, our calculations that we're going to go through are only valid if we measure all the forces acting on the runner. So if there's any period of double support where one foot is not in contact with a force platform and the other foot is, that is an invalid region to look at doing the techniques that we're going to look at here. On a counter movement jump, we either need to have both feet on one force platform or two force platforms with one foot on each force platform, and then we add up those forces afterwards. Or, which is not ideal, but you can put one foot on the force platform, one foot off the force platform, and then double the force platform if you think the movement is symmetrical. That is, that you think that the left and the right sides are going to be creating similar forces. That's not always a good assumption. So that is one technique that I try to avoid when doing this type of work. But the key is you need to measure all the forces acting on the person. Gravity is acting on the person. Although we're not measuring it, we can measure it ahead of time if we know what the body weight of the person is. So that's a constant. And that's it. So as long as those are the forces acting on the person, then we're good to go. Okay, so you should have watched part 1 and part 2 of this process. And so now we're actually in the computational part of determining position, velocity, and acceleration of the center mass during the counter movement jump. So these are the data that I posted. And down here is the vertical ground reaction force. And again, this is what would be measured. I have these dots here. I've used those dots in exams. This would be A, B, C, D, right here it is over here. But this is a ground reaction force, very characteristic of a counter movement jump. This is starting at body weight, then forces go below body weight, ground reaction forces go above body weight, and then this last section, ground reaction forces are below body weight again. All right, so let me see if I can insert. So if this is body weight right here, if I draw a straight line across, okay, we can see where forces are either above that line, above body weight, or below that line. Now, this is all predicated on the instructions for the person doing this jump was to start in a stopped position. They're not moving. And then they're told to start moving and do the counter movement jump where they go down, back up, and then they leave the ground. All right, so the trap a lot of people fall into is they start interpreting the forces as position, and that's incorrect. In order to get position, we have to pass through acceleration and velocity. And so we need to do a little math, and you're going to see that as we go along here. So here's our ground reaction force. And again, by watching part 1 and part 2, you'll know that first we need to subtract out body weight from every data point, then divide by mass, and then we get acceleration of the center mass. And you can see the acceleration of the center mass follows the same exact pattern. That's because body weight is a constant and mass is a constant. Therefore, the only thing that's varying is the ground reaction force, this right here. That's what's on this axis is the ground reaction force. So if that's the only thing that's going to vary, then acceleration is going to vary just like the ground reaction force. And here's, just to confirm, there's 0 acceleration. That'd be analogous to body weight. So when the ground reaction force and the body weight are the same amount, that numerator of our equation is going to be 0. So divided by mass, that's going to be 0, and acceleration is going to be 0. All right, so now we have periods of negative acceleration, periods of positive acceleration, and a period of negative acceleration. Again, the tendency is to incorrectly start interpreting this as downward and all of this upwards. That is not correct. All right, and now let me show you the equation. Here's acceleration right here. Force, the ground reaction force in this column, subtracting out body weight, and all I did is I copied body weight all the way down because that's a constant. This is the ground reaction force. This is what the force platform is measuring. So F14 minus G14, that's the numerator, divided by G14, body weight, divided by 9.8. That's mass. That's what is going to give us our acceleration. All right, and that's just from the equation, F equals ma. Add up all the forces acting on the object, these two, we get the product of mass and acceleration. And I just moved mass to the other side of the equality sign. All right, so that's the equation, and it matches what we covered in part 2, and that gives us our acceleration profile. Now we need to integrate from acceleration up to velocity. All right, and this is what our velocity profile is going to look like. Here's 0. Let me move a thicker line up here so you can see where 0 is. Here's 0 velocity. These are negative velocities. These are all downward movements. All downward movements up until this point. Once velocity becomes positive, it's a vector, and that positive velocity is indicating upward movements. So now we interpret this as speeding up, moving downwards, slowing down, moving downwards, speeding up, moving upwards, and slowing down, moving upwards. And right there is takeoff. So you see we actually have a little bit of slowing down right before takeoff. Ideally, we make that as little as possible, and that can be a technique, it could be an equipment issue, it could be a shoe issue, what have you. All right, so now let's look at our equation for integrating. Here's our velocity data right here that's plotted. So now the equation is right here. Acceleration times the time interval, which I have set up as 1. Why do I have it as 1? That's not correct. Oh, okay. Sorry. I should have looked at my equation ahead of time. Whew, all right. Maybe I should edit the video, but I won't. All right. So I have 1 over 1008, and I was looking at the 1 independent, and I should not have. The time, the delta t, is this part right here. I'll put it in the parentheses now. 1 divided by the sample rate. That's the time interval. That's the width of the acceleration rectangle that we talked about in part 1 and part 2 of this video series. And then I'm adding K14, K14. I'm adding the previous velocity, all right? That's the VI. We're solving for VF for this one small rectangle that is 1 over 1,008 second, okay? So 0.001 roughly. All right, now notice the very first data point I have pointing up here to the very first velocity, and this is predicated on the instructions I've given to the subject, stand still and then start moving. And as long as the person was standing still as I'm collecting my data, then I can put 0 in here. And I'm going to show you how this, if we make a mistake or we give the wrong instructions or the subject doesn't follow the instructions, this is going to change everything. going upwards. All right, but down here, every final velocity is predicated on the initial velocity before it. And then that final velocity becomes the initial velocity for the next rectangle, if you will. So A delta t, here's the delta t here, 1 over 1008 plus initial velocity. That's our velocity. That's our integration to determine, integration of acceleration to determine velocity. Okay, so now we're going to integrate the velocity profile to give position. All right, now here's position. So again, I have velocity, k14, times delta t, 1 over 1008, that's the sample rate, plus the initial position, which right now I'm setting at 1. If I go to the next cell, you'll see here, it's velocity, v, times delta t, 1 over 1008, plus the previous cell. That's the initial position. And then this is the final position. And then that equation just carries down all the way to the end. All right, so now I have, in essence, this would be my starting position, 1, and now I have downward movements and upward movements. That point where a transition between downward and upward is right here, where it passes through 0. All this lines up nicely mathematically. It has to. It has to. Because one plot determines the other. And in fact, if I take this position data set and then I take the derivative of that, I'll get exactly this. And if I take the derivative of that, I'll get exactly this. So everything has to match up mathematically. All right, so that's my plot. Now, the mistake a lot of people make, as I said, is they try to interpret position from this plot. And they'll often say, oh, this is the lowest position, or maybe this is the lowest position. Well, neither of those are necessarily true. So here, acceleration is negative. Velocity is speeding up, moving downwards. We haven't even reached the lowest position. And likewise, if I move over here to the peak ground reaction force, that's the peak acceleration. That's in a period where velocity is actually positive and the person's speeding up, moving upward. So it's not the lowest point. That peak, even though sometimes I draw it so it shows up at the lowest point when I do my PVA sketch, it doesn't need to be at the lowest point. It's wherever there's the greatest rate of change of velocity, which is the greatest acceleration, which is the greatest ground reaction force. All right, so that's important to remember. The other thing I like about this spreadsheet is then I can change the initial parameters. And what I'm going to change right now, because the one that really matters, is initial velocity. That very first velocity that we tell our subjects to stand still, and then we collect data. If they're not standing still, watch what happens. So I'm going to change this initial velocity. I'll just change it to 0.5. See what happened? Nothing changed down here. Nothing changed on the ground reaction force. Nothing changed at the acceleration profile. You see how that velocity is now shifted upwards? Because that's shifted to 0.5. Well, look what happened to our position plot. All right, let me do Control Z. I'll go back to 0 velocity. Watch the position plot. See how that shifts? Notice also the pattern of velocity is the same. It's just moving upwards and it's shifting based upon that initial velocity. And that shift causes a shift in position data. That's huge, all right? And that was just changing a little bit. And likewise, if I go in the other direction, negative 0.5, now that pattern shifts downwards. And look at what happened to my position plot. Okay. And if I go to 0, that's what it should be. This is negative 0.5. If I go back, that's, oops, sorry. That's what it should be. And then the pattern stays the same, but the position data changed dramatically. So what's happening? Well, this is an error. Either the person was moving. When we start to see some weird shifts in position, when we do this process, we need to suspect that something's wrong with that very first velocity. All right. That's really important. This is why when you do this type of work, you really need to tell your subject, stand still, and you need to start your data collection and then say, okay, go. So you need that period of time where the person's standing still. And if they're not standing still, then all your data are going to be off. If you also have the incorrect body weight entered, all your data are going to be off. And so that's important to know what body weight is. And here's where I'll shift gears, I'll go to Matlab in just a second. I do not use the scale, the independent scale, to measure body weight for this type of work. I'll use the force platform, and I'll actually incorporate this measurement within this data set. So let's do that. Let me switch gears to Matlab. And what I'm actually going to do, and so yeah, you can see these dots here. You can see how it's fun to ask what's happening kinematically at each of these points, and then you have to try to interpret them. All right, so now let's switch to Matlab, and what I am actually going to do is use a different data set, because the problem with this data set is I don't have anything before or after the data here. And so this spreadsheet was put together based upon data that were extracted from the moment the movement started to the moment that the feet left the ground. I actually wanted a data set for Matlab that includes more of the raw data. So let's go to Matlab. All right, here's Matlab. All right, so now I can walk through the code here, but what I'm going to do is read in a unique data set that's different from the one that's in the spreadsheet, and then I'm going to process it. Let me show you what the program does, and then we'll come back and go through some of the code. And I'll post the code if you like. All right, so here's the raw ground reaction force data. FZ on the y-axis, time on the x-axis. All right. And I'm just working with FZ here. So here's our count of movement section. Here's flight, and then here's landing. Now, I may be interested ultimately in landing parameters, but in this case, based upon what we're talking about now with adjusting the ground reaction force to yield PVA, I'm going to extract just the jumping data for analysis. All right, so first, I am telling the user to click in the body weight region because I need body weight for my equation, F equals ma. If we add up all the forces acting on the object, we get mass times acceleration. Hopefully you can see that. That red region represents the calculation of body weight. And you can see how that's a nice straight line. That's because when these data were collected, the instructions were to stand still. And then what I do processing-wise is I'll take an average body weight for maybe a 1 second period, or depending on how long the pre-movement data are. And if I start to see any oscillations in this region, then I know I have a problem, because that means the person was not standing still. And that also tells me that my equations where I set the very first velocity to be 0 are all going to be off because the person's moving. All right, so what do I do next? I want to extract just the jumping phase, so I'm going to click during the flight phase. So anywhere in here. So programmatically, what I'm going to do is I'm going to search to the left of wherever I click to identify takeoff. All right, now if I wanted to do landing analysis, I would click here and then I would extract the data to the right of this click. I can click anywhere in here and then it will pull out the data to the left. All right, so what do I have here? Now I've got 4 plots. Down here is ground reaction force versus time, acceleration versus time, velocity versus time, and position versus time. Notice the time axis I did not reset because I wanted to show you that these are extracted data. If I'm processing these data, however, I would restart this data point, the very first one, at time 0. And then this last data point will be the time of takeoff. This 3 seconds is an arbitrary 3 seconds. It all is based upon when I hit the start button to collect data and when the person started moving. So this time, these times down here are meaningless. It's more meaningful to adjust the time axis and make this very first data point that I'm extracting time 0. All right, so now I have ground reaction force. That's that same general profile. You see it looks a little different than the data we were working with in Excel. But in general, it has some ground reaction forces that are less than body weight, where body weight is the very first data point. And we have ground reaction forces that are all greater than body weight, reaching a peak ground reaction force, and then ultimately takeoff. And you see these oscillations in here, those look different than the previous data set we were working with. These oscillations can sometimes come based upon our instructions in terms of, are you going to jump? Are you going to tell someone to jump as high as possible? Is it a submax jump? Or are you going to let them use their arms or not use their arms? All of those factors will influence the shape of this ground reaction force. We adjust the ground reaction force to get acceleration. Here's 0 acceleration. These are all negative accelerations. These are all positive accelerations. Peak acceleration, and then acceleration at takeoff. Negative 9.47. Yeah, it should be negative 9.8, right? All right, so we know there's already maybe a little bit of error in here and that we need to deal with at some point. Then integrate the acceleration profile. All right, all negative velocities up until acceleration becomes positive, probably right somewhere around here. And then these are all positive velocity, speeding up, moving upwards, peak velocity here, and then a little bit of slowing down right before takeoff. A mistake a lot of people will make when calculating jump height from velocity is they'll identify this peak velocity and then calculate jump height off of that. That's incorrect. Why? Because you actually slow down a little bit right before takeoff. That's the velocity you need to use to calculate jump height. And then we integrate velocity, we get position data, downward movement, upward movement, takeoff. And notice that takeoff position is a little higher than the starting position. That's in large part because you have some planar flexion at takeoff, whereas in the starting position, you're in a neutral position at the ankle. But this could also be higher if you're using the arms, and the arms are above the head, whereas here maybe they're down at the side. So those are factors that will affect the center location of the center mass. All right, now notice here's peak ground reaction force, and that's nowhere near the minimum position. And how cool is that, right? This peak ground reaction force occurs at the peak acceleration and occurs at the greatest rate of change of velocity. So the steepest slope of velocity, which is right in this region right here. And that's right near takeoff. Okay. All right, so that's what this program will yield. And you see how quickly I did that because I put all the code in. Now, what I would do is if I'm processing lots of data, I would just change my file that I'm reading in, and I'd be able to do this all right away. Do a loop of the number of trials or conditions I have of this type of data set. And from that data set, I can also start doing things like calculating or identifying peak ground reaction force. I could do loading rate or unloading rate. I could do average force. I can do peak accelerations, peak velocity going downward, peak velocity going upward, range of motion of the center of mass, all different things. We can build that into our program really easily, okay? All right, so let's look at the code. And I'll post it, and if we want to go in more detail, certainly let me know. I always start with a clear that clears all the variables in Matlab. I also clear the screen, and I close any figure that may be open. That's just standard code that I use to clean up before processing. Then I set parameters, my initial position being 1. That's just an estimate of where the standing center mass height is. If I don't know what that is, I can leave it 0, In fact, if I leave it 0, all you see is everything will be the same, except the position plot will start at 0. So I got to click there, I got to click there. Now we're starting at 0. I still have downward movement, I have upward movement, but now I've got negative positions, all right, which is fine. You know, I can still figure out this displacement based upon the algebra, but and so the initial position of position is not that critical. What is critical is this initial velocity being 0. If that's not 0, then everything goes sort of haywire. All right, so there's the initial velocity, body weight. This is a number of data points I'm using to average. So I know the sample rate was 1,000 hertz, so this is taking 1 second worth of data. FZ start, this is a force criteria that I use to identify the start of the movement. So I look at the ground reaction force and look for the first data point that falls 20 newtons below body weight. You have to be careful with this criteria. It depends on the type of movement and what you're allowing the subjects to do. One time we were doing a standing backflip, and to initiate the movement, the person actually moved the arms upward. That increased the location of the center mass superiorly, and that changed how we were extracting the data, because now the ground reaction force was actually going in a different direction than what we expected. And so we had to adjust based upon using the arms and how the task was being done. So this is not an absolute criteria that you should use every time. This is FZ takeoff. This is a very common force value to use to identify takeoff. You do need to be careful and look at the amount of noise that's in your force platform. Sometimes your noise may exceed 20 newtons, and that can wreak havoc on the technique for identifying takeoff. And there's some alternative ways to do takeoff. But right now in this program, I just did a quick one and looking for the first force that falls below 20 newtons. Sample rate 1,000. Here's my data. I'm reading that in. And then I'm assigning the variables. This data set actually has right data and left data. And then I just add those two up. And then from there on, I'm only analyzing the total ground reaction force. And then I created a time column, 0 to 1 over the sample rate. So that's the interval. And all the way to the end, the length of the variable or the data set, -1 because I'm starting at 0. So I have to take off 1 point and then divide all that by the sample rate. So first thing I do, determine body weight. I plot the data, time versus FZ. And then I click in the body weight region and I use that G input function. I have to do some rounding to make sure that I'm getting a whole number, because I know I'm going to access an element of the vector in Matlab. And then I'm looking, ultimately I'm dividing that range I set above 1 second. I'm dividing that in half. So wherever I click, I'm going to look a half second before that click and a half second after that click. And then I calculate that body weight based upon the mean from where I clicked 1/2 a second before and 1/2 second after. And I plot that out in red. And I always like to do that because then I can make sure that my program's operating correctly and I'm doing exactly what I'm expecting that I'm doing. And if that red line shows up in a weird spot or it includes some data, so for example, if I click too close over here, look at that, that red line includes some of that. So I don't know what's going to happen with PVA. All right, it looks somewhat similar. All right, maybe some little differences here in position, but now that I guess highlights even the concern that I was a little sloppy with identifying body weight. I got some data that look reasonable, but are should not be correct. So now I need to watch out for that. And so that's the advantage of plotting out where you are picking body weight. So if I'm going to go extreme and look over here, it's interesting. The average of that may actually still be pretty close to. Oh, now it's obviously off. Okay, so clicking in the wrong spot is going to make a big difference because you're calculating the wrong body weight. What I'll often do in a program is, if I'm using this, I'll export the body weight that I calculate, and then I double check that every trial has a similar body weight. And that's a good way to debug things that might go wrong in your program or in your data collection, where maybe the person wasn't fully on the force platform, or maybe they weren't standing still, things like that. Okay, click during flight. This is where I'm going to extract out the data, really just the jump phase data, and I'm going to find where takeoff occurs. Here's where I find the start of the movement. I find where ground reaction force is less than body weight minus the takeoff. So sorry, this, just to make it clear, I should do this. All right, I'm looking for where the ground reaction force is less than body weight minus 20 newtons. Okay. I use takeoff here. It's the same criteria. What should I should have used start. I was lazy. I think I changed that halfway through my program. Okay. Sometimes you want a different criteria for the start versus the takeoff, and that's fine. Remember, when you write a manuscript or an abstract, you ultimately just need to explain to the reader the criteria you use to identify the start and the criteria you use to identify the takeoff. They do not need to be the same. Just to let the reader know, so the reader can agree or disagree with your criteria. So then what I do, just a little trick, I used the start of the movement to be the very first data point that falls below 20 newtons, okay? And knowing how this find function is important. Find where data set ends, or find where the takeoff is. And now this looks a little tricky, but I'm gonna find where the ground reaction force from 1 to X end, which is where I clicked. So I'm only gonna search from the very first data point to where I clicked. So wherever I clicked in flight phase is going to be included in this find. I'm going to find where all the data points are greater than the takeoff criteria, the 20 newtons. And then I take the very last data point, which represents the last data point that was greater than 20 newtons. Okay, so just a little trick. I could have made this a less than and then used the first one. There's different ways to do it, but that was the way I did it for this one. Okay, then I extract the data from start of movement to the takeoff. So here's takeoff, here's start of the movement. So I'm extracting the ground reaction force. I'm creating a new time, actually I'm not creating a new time column, but here is the time from the original time column, and I'm just extracting those data as well. All right, so now that the PVA part, so that's just getting the ground reaction force ready to go. Here's my acceleration in the Z direction. FZ, counter move and jump, which is the extracted data, minus body weight, times, divided by body weight divided by 9.8. That's mass. That's our same equation that we went over in part 1 and part 2, and what I showed you in Excel. I just put a dot there. That's just habit. Scalar math is different than vector math. And I just get in the habit of, when I know I'm doing scalar math, which is element by element math, that I always put a dot in there. So it's just a Matlab habit I have. All right, now we're going to integrate the acceleration process. That's calculating acceleration. We're not integrating the ground reaction force. We are using the ground reaction force to calculate acceleration. All right, now we're going to integrate, and we're going to loop from the second data point of acceleration to the end, or to the whole length of the acceleration vector. Why start at 2? Because I'm setting the very first acceleration to 0, because I'm telling the person not to move. Okay, so that is one of our criteria here, and let's make sure, and I know I took this out, so let me put it back in. A1 is 0. Okay, that's initial acceleration. I only wrote this program this afternoon, so sorry, still cleaning it up a bit. All right, so integrating. So it's going to start at the second the second velocity point, because that's V2, the second element, V1, sorry, let me go back up here. V1 is set to 0, and S1 is set to 0 too. So V1 is set to 0, that's already known, and now I'm starting at 2. And now I'm going to multiply the acceleration at element 2 times the time interval from element 2 to element 1, which time 1 is also 0, plus Vi minus 1. Okay, so that's 2 minus 1, that's V1. So V1 we specified to be 0. So that's where that comes in. And then we're in a loop. And so if this ends up being, if I is at the 55th row, this would be calculating V55, that element. We're going to use the acceleration at element 55 times the time interval from 55 to 54, which is set. I could have put in 1 over the sample rate, plus the velocity at V54. That's the initial velocity. And this just loops all the way through to the end of the acceleration vector. We do the same exact thing for position. From 2 to length, it doesn't matter. AZ and V will have the same length, so I could put V in here if I wanted to. It doesn't matter. They're the same length vectors. And the position plot will also be the same length. So I'm going to calculate from S2, the second element, I'm going to calculate that as the product of velocity at element 2 times the time interval between time 2 and time 1, which is 1 over the sample rate, plus the position prior to row 2, which is S1, which we specified up above as 0. And then I go down and I loop all the way through, and I go down here and I just plot those again. I plot position, velocity, acceleration, and ground reaction force. We use ground reaction force to calculate acceleration. We integrate acceleration to get velocity. We integrate velocity to get position. And then I did calculate height here. I don't know what. Oh, 2.2. That's wrong, right? Because that was the bad data set that we used. All right. In fact, why don't we look at, maybe I can do a print F1 height equals, oops, yeah, I'm going to do that. Print F1 into string, and this is just a little trick. Print F likes to print character arrays versus integers, so I'm going to put in height here. Into string is a function you're going to want to use, and then I'll actually put in an extra carriage return here, so it looks nice. And now I'll run it again. Hopefully it works. Okay, find body weight, click in the flight phase. Yeah, because I used the wrong /H, /N height. Save that. That was just my thumbs not working. And oh, height is 0. Oh, okay, I need to mess with that a little bit. Height is not 0. Height is 0.2968. So I've got to multiply this by, my quick way is multiply by 10,000. Oh, well, I'm not going to spend time on this, but you got to trick Matlab to show what you're interested in showing. So that would be 2.969. Oh, that's still not, no, it's 29.69 centimeters. So 0.2969 meters, all right? So 0.2969 meters, okay? All right, I shouldn't have added that in, but that's okay. I can fix that and when I post it. Okay, so that's using Matlab. Now, again, I'll go back and show the importance of initial position. So now if I make this a ridiculous number like 2, that the person's moving 2 meters per second, which would be about 4 miles per hour, prior to starting. This is what's going to happen to the data. It's going to look all wrong. The ground reaction force is the same. The acceleration profile is exactly the same. The velocity pattern is exactly the same, but it's starting at 2. And there's no negative velocities, meaning that all there is upward movement. And that's what this represents, is all upward movement until takeoff. Obviously wrong. There's no counterpart to this counter movement. But everything looks good here. Everything looks okay here. The pattern looks okay here. It's just starting at the wrong value. So if the person does not start with 0 velocity, then we're off. We're going to be off. We are not going to be able to process the data to get to position or even have good velocity parameter. We got velocity pattern, but we don't know this magnitude obviously is wrong. And then the height is just going to be 1 meter. Okay, not a ridiculous 1 meter. Some people can jump that high. All right, but it's obviously off what we had already started. So this initial velocity is really, really important. And when you collect your data, it's really important to make sure your person is standing still. Now, there are some tricks. If we don't know that velocity, there are some math tricks that we can do to ultimately still do some integration, but I'm going to skip over those right now. All right, I think that covers it. Hope this helps, and hope you have fun programming. Again, this is a great way to process all your data if you're doing a counter movement jump, and look at every data file and plot it out and make sure it's all good. Okay, thanks everybody.